In this video, I want to explain what real numbers are. You might think you already know them because you've been working with real numbers a long time, but there is a subtlety that I want to describe and then explain, what is the actual definition. So, I'm sure you've seen examples. Square root of 2 is 1.4142, etc. And then dot dot dot, pi is 3.1415, etc., etc., etc. But the question here is, what do these dots means? Well, I'm sure you know the answer to that. There are infinitely many more digits here. So a real number is essentially some digits and then a dot and possibly another infinite string of digits. But that raises the question, okay, even if you put infinitely many digits here, what would it actually mean? Okay, so we know what the natural numbers are. We know what the integers are, and then we know what the rational numbers are. Basically, they're written as fractions of integers. But then what's this here? Well, we can understand this part. That's a natural number. And 3.1, that's a rational number. That's just 31 over 10. 314 over 100. 3141 over 1,000. So what you see here is, if it wasn't for these dots, then what I'm looking at is a rational number. And every time I write down one more digit, I get another rational number. So what you're seeing here is that when you this sequence, so here you have an infinite sequence of digits. That may be tricky to understand what that actually means, but we can take finally many digits, and then one more, and then one more, and then one more, and then we get a sequence of numbers, 3, 3.1, 3.14, etc. So the way you should read these dots is that this here is actually a sequence of rational numbers. So the sequence is 3, 31 over 10, 3, 114 over 100, 3, 1, 4, 3, 1, 4, 1 over 1,000, and so on. So here we have an infinite sequence, say x1, x2, x3, and so on, and of rational numbers. Okay, they're all rational numbers. Now, what exactly would this number be then? The number with these dots in it. Well, this number with these dots in it, I can translate that into a sequence. But the sequence also has dots in it. But at least I can understand every member of this sequence, because every member of the sequence is a rational number. Okay, a rational number, rational. So I can translate this into an infinite sequence of rational numbers. And now you know from calculus that the limit of this sequence is pi. But of course, that's a little bit circular reasoning, because that still doesn't tell me really, how this is really defined, right? So that still leaves the question: what does this mean? Okay, but you are seeing at least a little bit of an answer. This concept that you've been working with a long time, but that until this math class you've never seen a definition in prior math classes of real numbers. But what you can see in this example is that this concept can be translated into this concept. So the concept of real numbers can be translated into it can be presented in terms of sequences of rational numbers. So what I want to do now is I want to start with the rational numbers, and rather than assuming that I already know what real numbers are, which is what I did here, instead of assuming that I already know what real numbers are, I want to actually construct the real numbers in such a way, and I want to construct real numbers in such a way that the limit of this will be that, just like what we expect. So, in order to construct real numbers from rational numbers, I'm going to look again at this example, and what I see here is a sequence. Now you might say, oh wait, this sequence converges and that's the limit, but that's circular thinking, because if you say that this converges to pi, then you're already using the reals. Okay, so if I'm starting with nothing but rationals, if I don't have the reals yet, then this doesn't converge to anything. You see, if I don't already have the number pi, then this doesn't converge to anything. This only converges if I already have constructed, if I've already shown that this number exists. Only then can I say that this converges to that. So if I can't say that this converges to that, I mean, I can say that when I'm done with the construction, but until that point, I cannot say that this converges to that. But then I still want to somehow work with sequences like this, but I'll just need to have a different description. So, saying that this converges means I need this sequence as well as its limit. So I want to change the definition of convergence a little bit, so that I don't rely on this, and so that I don't rely on circular reasoning. And the definition then that we'll use is called Cauchy sequences. So what's a Cauchy sequence? So let me remind you, what is the definition of a convergent sequence? A convergent sequence gets arbitrarily close to some limit, and that I cannot use because I cannot say that this has a limit without circular logic. Okay, so a Cauchy sequence, rather than getting closer and closer to a limit, a Cauchy sequence is one where the numbers get closer and closer to each other. Okay, so how would we define that? For every epsilon, there is a tail such that everything in that tail is epsilon close to each other. Okay, so there is a tail of the sequence such that all members of the tail are epsilon close to each other. So if you forgot what a tail of a sequence was, I can rewrite this as follows. So if you have a sequence, then the tail is just throw away the first n terms and keep the rest. So, or let's say if I throw away the first n minus 1 terms, then I'll get these. So for some n, you throw the terms x1 up to xn minus 1 away, and you keep what's left, and that's called a tail. So how would I rewrite this without the word tail? Well, for every epsilon greater 0, there is some cutoff point n, such that everything in this tail is epsilon close. So for every I and j greater equal n, so for every I and j in the range n, n plus 1, etc., if I take the ith term and then take the jth term, then the distance between them is less than epsilon. Okay, so that's the definition of a Cauchy sequence. So why do I want to use Cauchy sequences instead of saying convergent sequences? Because if I want to say that this sequence is convergent, the only way I can say that is if I already have this number pi. Because the definition of a convergent sequence, the limit is built into the definition. So you can't say that this converges unless you already had this number pi, and that's circular logic if I'm trying to construct real numbers. Now, but this definition, I can say that this sequence meets this definition without knowing about limits. Okay, so this here is an example of a Cauchy sequence. So why is that true? Well, you can basically see that these numbers keep getting closer and closer. So if you choose some epsilon, say epsilon is 10 to the minus, say 50, okay? Then throw the first 50 or 51 terms or whatever. Let's throw the first 60 terms away of this. But then the numbers get so close that the distances between them will be less than this. Okay, so if I throw away the first 50 or 60 terms, then I'll have something that looks like some big number divided by, I don't know, 10 to the 60. And then the next term in the sequence is some big number divided by 10 to the 61. And the distance between these two is on the order of 10 to the minus 60, which is less than epsilon. Okay, so no matter how small you make epsilon, there will be some cutoff point such that beyond the cutoff point, everything gets really, really close to each other. Okay. Now, if I do some forward thinking about where I want to end up, if I already have real numbers, then a Cauchy sequence just becomes a convergent sequence. But right now I can't say that because I'm presuming that we don't have real numbers yet. I want to construct real numbers. So if I don't have the real numbers yet, but I do have Cauchy sequences like this one. Okay. So then what can I do? Well, let's take all Cauchy sequence. So take all Cauchy sequences. So sequences x1, x2, x3, etc. For which all of these guys are rational numbers, and so for every I, and the sequence is Cauchy. Okay, so in other words, every sequence of rational numbers that meets this definition, every such sequence is an element of this set. So for example, okay, so let's give this set some name. Let's call this okay, this is a really big set, so let's call it capital M. Okay. So for example, this sequence that in the previous example, so here I have an infinite sequence, and that whole thing is just one element of M. Okay. But now you might wonder, okay, I might have two sequences that get really, really close to each other. So for example, let's make a different example, and let's look at this one for inspiration. So let's make sequence number 1, which is like this: 1, 1, 4 over 10, 1, 4, 1 over 100. 1, 4, 1, 2 over 1,000, and so on. But now let's make another sequence. Let's just say I take just some of these terms. So let's say I take my denominators to be not 1, 10, 100, 1,000, but let's say I take my denominators to be 1, and then 100, and then 10,000. So that would be 1, 4, 1. Oh wait, this would have been a 4. okay, etc. So in other words, this second sequence is basically is the first sequence where you basically drop this guy and this guy. So it's still an infinite sequence, but basically all the even number terms are dropped, and I'm keeping only. So this is just the odd numbered terms of the first sequence. So in other words, if S1 was x1, x2, x3, x4, and so on, then sequence number 2 is x1, x3, x5, x7, and so on. Okay. Now, now both of these are Cauchy sequences. You see, these numbers keep getting closer and closer together. So in other words, this is a Cauchy sequence. But this is also a Cauchy sequence. These numbers also get closer and closer together, but they also get really, really close to these ones. So, so I'm now going to define an equivalence relation. We'll just say that S1 is equivalent to S2 if... so this is an equivalence relation. If for every epsilon greater 0, there is some cutoff point such that beyond the cutoff point the sequences are epsilon close. So that for every n greater equal n, the nth term in sequence 1 is epsilon close to the nth term in S2. Okay, so if so if the nth term in this is really close to the nth term in this, yeah, so if for every positive epsilon, some tail of this and a tail of this, they all get epsilon close to each other, then we say that the sequences are equivalent. So let's give an example. Maybe a little bit of an easier example. Let's say sequence sequence T1 is this. Let's say 9 over 10, 99 over 100, 999 over 1,000, 9999 over 10,000, and so on. Hopefully you see the pattern. And sequence number T2 is this sequence, 1, 1, 1, 1. And now notice, this gap is small, but this is even smaller, and this gap is even smaller. So, so the 100th term in T1 is really close to the 100th term in T2. Okay? So sequence T1 is equivalent to sequence T2. Okay, so so if you take so how would you prove this statement? So if we take any epsilon, so I'll just do it by an example. So let's say epsilon is say 10 to the minus 100. Well, if I now skip say the first 110 terms here and here, then they will definitely be closer to each other than this. Okay, and this argument would have worked not just for this epsilon, but for any epsilon. So for any epsilon, this requirement is met. So here you have an example of equivalent sequences. Okay, so equivalent sequences, they get arbitrarily close to each other. Now then in the next thing, I'll just scoot this over a little bit. Let's make sure it's still visible. Now in the next thing, remember from chapter 1, if we had a set and an equivalence relation, then that equivalence relation partitions your set. So then you get a partition. So let's say here is the set M, and you get a partition where everything that is everything that is equivalent, everything that satisfies this equivalent relation, they all are in the same class. So, for example, S1 is equivalent to S2, so S1 and S2 are in the same class. But there are a lot of other sequences that are also in that class. Okay, and now sequence T1 and T2 are also equivalents, but they are not equivalent to that. So T1 and T2 are in a different class than S1 and S2. So these are not in the same class as these, but these two are in the same class. Okay, so then every Cauchy sequence falls inside a class, but that class always has a whole lot of sequences in it. Okay, so and then these classes are called equivalence classes. Okay, so now this notation is the set of equivalence classes. So, for example, if I take this class, the class T1 with T2, but this class doesn't just have T1 and 2, and so this has anything, any sequence equivalent to T1 is also in here. And this, so this one set contains this sequence, it contains this sequence, but it contains a huge number of other sequences as well. And all those sequences combined is just one element of this. Okay, so that's just because this notation refers to the set of all equivalence classes. So saying that this is in there is just saying that this is one equivalence class. So this equivalence class is this one right here. Okay, and now we'll use some notation. If I write a Cauchy sequence like this sequence, okay, if I write these square brackets around it, that means the equivalence class that contains this guy. So this is the equivalence class of T1. Now, the equivalence class that contains T2 is the same as the equivalence class that contains T1. So the equivalence class of T2 is, the equivalence class of T2, but that's actually the same as the equivalence class of T1. Okay. Right. Now, now that we have this object, you might wonder, okay, I still don't see any real numbers in here. Actually, we're getting really close. So the definition now is as follows. The set of real numbers is this set right here. Okay. Now, now let's look at an example. Let's say I write the following number. Say 3.141592, etc. Now you might wonder, wait, how is that an element of R? Well, remember, this real number defines a sequence, namely this one. Okay, so this real number defines a sequence, namely 331 over 10, 314 over 100, etc. So this gives a sequence. Let's call this sequence, say, P, right? So P is this infinite sequence. And now pi is the class of P. But you might say, but there are different sequences that also converge to P. So let's say I have a different sequence. So for example, sequence Q, I'm going to take 3, and I'm going to take 3 plus sine of 3, and I'm going to take 3 plus sine 3 plus sine of this last thing, 3 plus sine 3. So let me give you the pattern here. So x1 is 3, and xn plus 1, the next term is the previous term plus the sine of the previous term. And if you do this on your calculators, make sure you set it at radians. So now try to compute some terms in this sequence, and what you find, so q is this sequence, x1, x2, x3, and what you find is that the numbers in this sequence get arbitrarily close to this sequence. So therefore p is equivalent to q. Let's say these two sequences meet this requirement. But if p is equivalent to q, then that means that the equivalence class of p is the same as the equivalence class of q. So that means you can represent the number pi with different sequences. The number pi can be represented with this sequence, but it can also be represented with this sequence. Okay, so because of this equivalence relation, each equivalence class can be represented with multiple sequences, and each of these sequences represents the entire equivalence class. Okay, so one of these equivalence classes has this sequence in it, but also this sequence. And now what exactly is pi? Well, pi is the entire equivalence class with this sequence in it, but also the entire equivalence class with this sequence in it. So that's that's what real numbers are. Now let's go back to this sequence. Okay. So what does this mean? 0.99999, etc. Okay. Well, I can apply the same strategy as I did here. Actually, let me just pull up this notation right here. So what does this refer to? Well, this refers to the class of this sequence. Okay. Now, what does this number refer to? Okay. And you see, so why does this refer to this sequence? Because you see, this is you see that's that element, and that's that element, and that's that element, and this is that element, and so on. So each time if I throw in one more digit, I get the next term of this sequence. If I do that here, well, this is that guy, this is that guy, this is that guy. So each time if I add one more digit, I get the next term in this sequence. So this here means the equivalence class of T1. And this here means the equivalence class of T2. But the equivalence class of T1 and T2 is the same. Okay? The equivalence class of T2 is the equivalence class of T1. So keep in mind the sequence T1 is not the same as the sequence T2. They're different sequences. But they are equivalent. Okay? This sequence is equivalent to this one because they they meet this where did it go? They meet this they are equivalent. They meet this definition. Okay? So they are equivalent, and since they are equivalent, then it means that their equivalence classes are the same. But this number here is just a short notation for that. And this number here is a short notation for that. And that's why they're equal. Okay? So they aren't equal because of some kind of, I don't know, magical description about what happens when you have infinitely many digits. The reason they are equivalent is because if you follow this definition, then that makes them equivalent. Okay, so there's no magic or deep understanding or whatever. It's just that if once you settle on this definition, that's what makes this equal to that. Okay. Now you might assume, wait a minute, I've seen proofs that they're equal, but those proofs are somewhat circular reasoning because they assume that you already know that what real numbers are. But that's the hard part to begin with. So the only reason that this is even a question is because people don't not always understand what real numbers are. Now, why don't they understand what real numbers are? Because nobody told them, right? So now that you know that the real numbers are this, and that you know that this is the class of a sequence and this is the class of another sequence, then asking whether or not they're equal is just a matter of checking if the sequences are equivalent. And if the sequences meet this definition, then they're equivalent. And if the sequences are equivalent, then their classes are equal. Okay, so now you know what real numbers are. Now you might wonder about this first example. You see, inside the rationals, this doesn't converge because this has no limit inside the rationals. Now, how would I know that this converges in the reals? Well, so let's say this sequence was this sequence, right? So I have an infinite sequence of rational numbers, and let's say it's this one. If there's no limit inside the rationals, how would I know there's a limit inside the reals? Well, that's actually very simple. Since this is a Cauchy sequence, okay, that means it's an element of M. Okay. Maybe I should just put this somewhere else. So this sequence, say 3, 31 over 10, 314 over 100. So let's call this sequence, I think I already named for that. Let's call this sequence P. So that's an element of M. So then the class of P is an element of this. But this is the set of all equivalence classes. But this here is the same as the rational, the real numbers. And so how do I know that this sequence converges? It's really simple. Just take its equivalence class. That's the limit. So the limit of a Cauchy sequence is its equivalence class. Therefore, every Cauchy sequence converges, and the limit is always an element of this. Okay? So so hopefully this explains, why limits of Cauchy sequences, why Cauchy sequences have limits, and why those limits are generally real numbers. Now, the fact that Cauchy sequences have limits also implies a lot of other key facts about the reals. So, for example, that if you have a subset of the reals and it has, then, for example, it has a supremum and an infimum. And so, for example, if A is not empty and if A is bounded from above, then it has a least upper bound, and that least upper bound is called the infimum. So I'll not prove that in this video, but the point is the fact that the real numbers have this property is really quite easy to prove once you know these things. So I think I'll just stop here.